Okay, so I'm sure that you guys will be able to see my screen. The portion that we have been given in this biochemical technique 624 is about a technique which is one of the very basic and fundamental techniques we use in biochemical research. Not only the biochemical research, but that's a very basic technique which is used in most of the discipline associated with biological sciences. So, as part of the course layout, we are going to discuss about UV and infrared spectroscopy. But I'm going to share a little bit of information about UV slash visible spectroscopy just to give you a better understanding of this technique. So UV visible spectroscopy is our first technique that we're going to start today. So let me start the lecture first. What is spectroscopy? Uh, in regard to this technique, you guys are aware of this technique at the level when you have done your, labs in your major as first year and second year. You have used uh, the technique of spectroscopy where you got the readings of the, ODs and you calculated that and you form the standard curve and all that kind of stuff. It's the same technique, but now we are going to go in a little bit of more detail to understand the principles behind this technique. So, spectroscopy is actually the branch of the science that deals with the study of the interaction of matter with light. So, we have light of specific values, specific wavelength, and all that kind of stuff, and how that light interacts with a material object. That's all about the basics of spectroscopy. You can also define that it is a branch of science that deals with the study of interaction of electromagnetic radiations with matter. So, why we are saying that electromagnetic, because when we talk about the light, and there are different regions of the light depending upon the wavelength. So that's why it's either interaction of light with the matter or it is interaction of electromagnetic radiations with the matter. So let's start first thing. What is electromagnetic radiations? As you guys might be listening the sound, the people are joining in the class, and as I requested earlier on, that this time I'm going to allow the people to enter the class late, but from the next time I'm not going to allow the participant to enter the class after 5 minutes because that's going to disturb the class. So be punctual and join the class within the time that is being allocated. Okay. Right. So now, what is electromagnetic radiation? Electromagnetic radiation is basically consist of small packages or discrete packages of energy bundles, which we call photons. The photon is being defined as a packet of energy, and the electromagnetic radiations are actually consist of these packages of energy, what we call photon. A photon is actually consist of a combination of electric field and a magnetic field, and both of these fields are oscillating. I'm sure that you might be aware of what is the meaning of oscillation. Oscillation is a particular movement of a wave. So a photon is actually a packet of energy which is consist of the combination of an oscillating electric field and an oscillating magnetic field. The important thing is that both of these, they are perpendicular to each other, perpendicular in terms of their direction. Now, in order to elaborate that what it looks like, we have this picture here. You can see that this is the source from where the light, whatever is coming, and this is the direction. And then you have the magnetic field with the purple and electric field with the green sheet. So you can see that this is perpendicular. The direction of the magnetic field and the direction of the electric field, they are perpendicular to one another. And that's how the photon are composed of. So going further, to define electromagnetic radiation, when you talk about the radiation or any kind of radiation, then it is moving from one direction to another direction, and it does have certain characteristics which needs to be defined. The first thing that we're going to define with the electromagnetic radiation is about frequency. This symbol is not actually V, it's a new symbol, a little bit curved, but that's how we write on the computer. So how we define frequency? A frequency can be defined as the number of times electric field radiation oscillate in 1 second. Because when you have a wave motion, they are gauged in terms of the number of oscillations or the number of frequencies per second. So we define frequency as the number of times electric field oscillate in 1 second, and the unit for the frequency to measure frequency is hertz. So you can see 1 hertz is actually defined as 1 cycle per second. So more the cycles per second, definitely more will be the frequency. The second important thing to discuss in electromagnetic radiation's characteristic is about wavelength, the sign of the lambda. How we define wavelength? It is the distance between the two nearest parts of the wave, or you can say a wavelength can be defined as the distance between the two trough or the two crest. When you talk about the wave motion have got a specific direction. It could be longitudinal, or it could be transverse. You might have studied about these two types. So wavelength is actually the distance between two trough or two crest. That is being defined as wavelength. Now this picture is going to explain you about this. Now this is the upper projection is called trough, and this lower projection is called crest. So distance between the two troughs or the distance between the two crests, that's being called as wavelength. So now you have got an understanding of what is frequency. That is the number of oscillations per second, and the wavelength, which is the distance between the two trough or the two crest. So now how we correlate these two characteristics? These two characteristics are correlated with the relationship, and that relationship is here. C is equals to nu lambda, where C is the energy. So as photon is subjected to energy, you can say that this E refers to energy, and this E is equals to h nu, or you can substitute the values either way, and that's how you can calculate. Now in this equation, you can see that there are few variables, and if you have all the variables known and one of the variable is unknown, you can calculate. Like for example, from this equation, E is equals to h nu. If you have got Planck's constant, which is a constant value, and you know the frequency, then you can calculate the energy. Similarly, here you can find out the other things, because this frequency is actually C upon lambda. So if you know the value of the C, you know the value of the wavelength, you can calculate about that. So this is the basic relationship of the variables when it comes to the knowing how to calculate the wavelength, how to calculate uh, frequency and energy and all that. This is a basic diagram to show you about the spectrum of electromagnetic radiation, and you can see that there are different regions, like in terms of the wavelength, in terms of the frequency, and in terms of the energy. Mostly we define this spectrum uh, on the basis of the wavelength. As you can see that from there to there, uh, starting from the gamma rays within the range of 10 to the power minus 13 to 10 to the power minus 11 meters. That's the wavelength. The unit of wavelength is meter. Then we have the next region is X-rays, then ultraviolet, then visible, which is a very small region here, then IR, then microwave, and then the radio wave. So starting from this side to this side, you have got different regions based on the wavelength, where you can define these electromagnetic radiations further into gamma rays, X-rays, UV, visible, IR, and microwave. Still, people are joining the class, and I'm again reminding that today is the first class, and we are allowing you guys to join, but not from the next class. So please be punctual and join the class on time. That's why I have shared the link well ahead of time on the WhatsApp group. Okay, so coming back, you can see that in this case of the wavelength, where we have got different regions, and these different regions have their specific name. Now, what we are going to study in this technique, as I mentioned the title, we are talking about the UV spectroscopy, which is ultraviolet, and IR spectroscopy, which is infrared. But as I said, that we will be discussing something about visible as well, but this is not the part of the discussion we are mainly focusing on. And then beside we have the microwave and radio wave. So, main criteria for defining them in generally we use is about, their wavelength. This is another diagram where it's being shown that an electromagnetic radiation or a white light is composed of further different segments. And if a white light passes through a prism, it's going to deflect or disperse into its seven constituent colors. So now this particular diagram right in front of you is actually the visible portion, the one that we discuss here, this one, just as this is a small portion. So this picture is actually the visible portion of the electromagnetic radiation, which is actually a white light. And this white light, if it passes through a prism, it's going to be dispersed or deflected in its seven constituent colors, as you can see, and they all have different wavelengths. So going further, let me start towards the basic principle of spectroscopy. Now, the basic principle states that it is about the measurement of the spectrum of a sample containing atoms or molecules. Like, for example, you will be given a sample, and that sample uh, contains some atoms or some molecules in them. It might be a solution or something else. This sample that is being given to you might be a colored sample or might be a colorless sample. So depending upon this, we have to think about that which kind of spectroscopy we're going to use, like the visible spectroscopy, and then the UV spectroscopy, and then the IR spectroscopy. But at this stage, we're not going in the details of this type. We're just talking about the basic principle. So the basic principle is that you have got a sample, and that sample would have some compounds in it in the form of atoms or the molecules. And we are interested in measuring the spectrum of that particular sample. So a spectrum is being defined as a graph, and this is a graph of intensity of absorbed or emitted radiation by the sample versus the frequency or the wavelength. So now in simple way, as I said that you guys have done this technique in your very foundation courses in first year and second year, where you have estimated proteins, you have estimated uh, carbohydrates, you have estimated many other molecules by using this simple technique. So when you have a sample, you have a source which provides you the electromagnetic radiation. That electromagnetic radiation will have a particular frequency and a particular wavelength. When this electromagnetic radiation passes through the sample, which you are interested in to measure, a particular amount of the light or electromagnetic radiation will be absorbed by the sample, and the rest is going to be emitted out. So when you measure that particular amount of the light absorbed by the sample, or you measure the amount which is being emitted out. Now, there are both the ways to calculate, because you know the amount of the electromagnetic radiation you are uh, passing on to the sample. So either you calculate how much amount of electromagnetic radiation has been absorbed, or reciprocally, you can also calculate or find out the amount of the emitted light. Both are the ways of doing the calculation. Now, you know the wavelength of your electromagnetic radiation, or you know the frequency. So when you have got both of these things, with the help of that, you can calculate the concentration of your sample. So spectroscopy is one of the very basic fundamental technique to measure the concentration of a particular compound in a given sample. So this is very, very basic principle. Like you have got a sample, it might be a carbohydrate solution, or it might contain proteins, or it might contain any other, molecule, and you are interested in knowing the concentration. So the first principal technique that you're going to use for this is spectroscopy. And as I said, the principle is that you have a light source, or you have an electromagnetic radiation with a known frequency and a known wavelength, uh, and you with a known intensity as well. And then this light or electromagnetic radiation will be passed through the sample, and the sample does have atoms or molecules, whatever, and they are going to absorb some of the light. So either you measure that light that is being absorbed, which is normally being, you guys are aware of the fact it's called OD, optical density. That's that's what the light is absorbed. Or you measure the amount of the light that is being emitted out. Now, depending upon this, you might have different instruments of spectroscopy where they rely on either measuring the light which is absorbed, or they rely on measuring the light which is emitted out. So in either way, you can use them. And then with the help of the known values and variable, you can calculate the concentration of that particular sample by making a graph, and what I was saying earlier on, the standard curve. You guys have done that already to calculate the unknown concentration of a sample. So this is the basic principle of spectroscopy. I'm sure that by that stage, everything would be clear to you. But as I said, if something you need to ask, we will have few minutes of the Q&A after the class. Now, you got the idea what is spectroscopy. Now, I'll go in a further detail. The type of spectroscopy that we discussed right now is being referred to as absorption spectroscopy, because what we are saying that when you pass on the light or electromagnetic radiation, a particular portion of that will be absorbed by the sample. So that's why we call it absorption spectroscopy. As I said, this is one of the very basic fundamental analytical technique which we use in our daily biological sciences experiment to find out the concentration. Now remember the spectrum that I shared, like for example, if we are using ultraviolet source of radiation between the range of 185 to 400 nanometer, or we are using the visible spectroscopy where we have the radiations within the range of 4 to 800 nanometer, and or we are using the IR spectroscopy where we are using the radiation source between 0.76 to 15 micrometer. Now, that is the choice. That is the thing that depends on what kind of sample we have, and then depending upon that, we have to either choose UV or visible or IR spectroscopy. There is another type, as I mentioned earlier on, which is emission spectroscopy. Now you got the idea what I was saying, that when you pass on the light through the sample, I told you that there are two methods of measurement. Either you measure the amount of light absorbed, which was absorption spectroscopy, or you measure the amount of the light which is emitted out after passing through the sample. And that's what we call the emission spectroscopy. Now, in our cases, the spectroscopic technique that we use might have the instrument which either rely on absorption or emission, but both of them are in practice. When it comes to emission spectroscopy, this is the same thing. It's an analytical technique where you are going to measure the emission of the radiation by a particle. And this is also being calculated to find out the unknown. The most common example of this kind of a spectroscopy is mass spectroscopy, which you all have heard of, right? Okay. So as in the beginning, I said that spectroscopy is actually the interaction of electromagnetic radiation with matter. So Let me cut down to the point where you understand that spectroscopy is mainly interaction of electromagnetic radiation with matter. That's the baseline of this technique. Okay, so let's go into further detail how this electromagnetic radiations they interact with the matter. So the first level of interaction is electronic energy levels. Now, what is electronic energy levels? When you keep something at the room temperature, the molecules will have the lowest energy level, and that is being referred to as E naught. Like, for example, you have carbohydrate solution or protein solution or anything else that you are interested in, and you keep the solution at the room temperature, that's the temperature where the molecules will be at the least energy, and that is being called as the E naught. Now, when you pass on the electromagnetic radiation through the matter, like in other case, this electromagnetic radiation is going to interact with the matter, definitely that radiation has got energy in it. So when the molecules interact with this electromagnetic radiation, they absorb some sort of radiation. Either it will be UV, visible, or IR or something like. So when the molecules absorb the UV visible light out of that electromagnetic radiation, one of the outermost electron present in the molecule will gain energy. And you know that when electrons gain energy, they move from low level to the higher level. So if they gain some energy, they will attain a little bit of higher energy called E1. And if the process goes on, it can go up and up and up to gain more and more energy. Now, this is being particularly referred to as electronic transition. So now, let me summarize. When the sample or the molecule are at room temperature, they have the minimum energy, the lowest energy, that's E naught. Now, when you pass on the electromagnetic radiation through the sample, the molecules will absorb some of the radiation. And as a result of that, the outermost electrons or the electrons in the outermost shell are the first one to gain that energy, and they increase their energy level from E naught to E1 and then E2 and then so on. So this transition of energy will be called as electronic transition. And I think you guys are aware of the fact that how to calculate this change of energy is very simple by the formula we studied earlier. It's energy is equals to h nu. H is the Planck's constant and nu is your frequency. And that's how you calculate the change of energy. And the change of energy can be final minus initial. So you can see that En minus E naught, where N could be 1, 2, 3, or whatever the levels are. So it's always final minus initial. So in this case, you can calculate the change of energy when the electromagnetic radiations passes through the sample. There is another kind of energy that we will be considering now. This was the electronic energy levels, and you see how when the electromagnetic radiation passes through the sample, increases the energy level of the molecule in terms of increasing their energies of the electron, and that's how you calculate the change of energy. There is another thing to discuss is about vibrational energy levels. Now, in this case, uh, there will be less energy level when electronic energy levels are there. Like, for example, when you compare the vibrational energy levels with the electronic energy levels, you can say that vibrational energy levels are with a less energy level as compared to electronic energy levels. What is vibrational energy level? We know that the material atoms, they are not stationary. Atoms will have their electrons, and all the time they are in a vibrational mode. And when they are in the vibrational mode, they would have some energy in them. So that's what we call the vibrational energy. So the spacing between energy levels from one to another, like from E naught to E1 and from E1 to E2 and so on and so forth, is relatively small between the range of 0.01 to 10 kilocalorie per mole. So in case when IR radiations, like you are passing on the IR electromagnetic radiation through a sample, and it is absorbed, the molecules are excited from one vibrational level to another, or it vibrates with a higher amplitude. Now, let me clarify what is the difference. In the first case, the electromagnetic radiation we were talking about was the visible, and it has got enormous energy in it. So when it passes through the sample, we saw the change in the electronic transition. While in this case, we have IR radiations having the energy to change the vibrational level, or you can say it increases the vibration of higher amplitude, like it increases the height of the vibration. So when in case of the IR radiation, the molecules will be excited because that's also energy. But that energy is not going to change their electronic level or electronic transition. This energy is going to change their vibrational level of the energy, or in simply increase the amplitude of the vibration. There is another change of the energy beside electronic transition and vibrational transition or change, and that's called as rotational energy levels. These energy levels are more quantized and discrete, and the spacing between energy levels are even smaller than vibrational energy levels. So if I compare all of these three, the highest level of the energy change is in the electronic transition of the energy, then comes the vibrational, and the least is of the rotational changes. So all of them are change of energy, but they have different methods, and they have difference of the change of the energy. So depending upon what portion of electromagnetic radiation is interacting with matter, it can either bring about electronic change of the energy level, or vibrational change of the energy level, or rotational change of the energy level. So I'm sure that you guys are aware of how the electromagnetic radiations interact with the matter, and as a result of that interaction, what kind of electromagnetic radiations we have used. Depending upon that, there will be a change in energy level. And that change in energy level would be of three types: electronic energy level, vibrational energy level change, and rotational. And you also understand the relationship that highest to lowest. The highest change or the difference between the two energy level is of electronic energy change, then vibrational, and the least one is the rotational change of the energy. Okay, now go on to discuss about two of the very famous laws that you already have studied again in your basic, first year and second year left when you did the spectroscopy, and it's being famous as Lambert-Beer's law. Now, it's Lambert-Beer law actually is a combination of two laws. Lambert law is separate and Beer law is separate, but we combine them because they are related to one another. I'm going to discuss them very briefly. There is some mathematical part in this presentation, but I'm not interested at this stage about the mathematical part. So you guys can also skip that. What I am only interested in is to give you a little bit of overview of these two laws, just to remind you of what you have studied about Lambert law and Beer law, and what actually these laws state. Now, the Lambert law state that when a monochromatic radiation is passed through a solution, now that solution is containing sample molecules or atoms. So when a monochromatic radiation is passed through a solution, the decrease in the intensity of the radiation with the thickness of the solution is directly proportional to the intensity of the incident light. Let me rephrase this in a more easier way. You have a source of radiation which is monochromatic. I'm sure that you guys know what is monochromatic, single wavelength, right? So we have a radiation source and we pass through a solution. That solution has got, some compound in it, some atoms and molecules. So The monochromatic radiation that you pass through the solution will have certain intensity. So the decrease in the intensity of the radiation with thickness of the solution is directly proportional to the intensity of the incident light. In other case, more the intensity of the light, more will be the absorption of the light. So if we say that let I is the intensity of the incident radiation and X be the thickness of the solution. Thickness means, you use the cuvette and all those kind of stuff and you determine that distance. So that law says that the small change in intensity and the small change in thickness is directly proportional to the intensity. And when you remove the proportionality sign, you introduce the constant. So as I said, I'm not going in the detail of the mathematical equation at this stage, but that's what I only wanted to shed light on what is actually Lambert law. Now I'll go to the Beer law and then I'll combine both of them. You got the idea, and some of you might recall from your early classes about these laws as well. So in Beer's law, it states that when a monochromatic radiation is passed through a solution, the decrease in the intensity of radiation with the thickness of the solution is directly proportional to the intensity of the incident light, as well as the concentration of the solution. Now, this particular law indicates that, for example, if I is the intensity of the radiation that you are using, and X be the thickness of the solution or whatever we call, and C is the concentration of the solution. Now, whatever solution you have been given, it must have certain compound and it must have certain concentration. So it says that the small change in the intensity divided by small change in X is directly proportional to the concentration. So that means if you have a sample containing carbohydrates or protein, it simply says that the more the concentrated solution is, the more light will be absorbed. So now I'm going to combine both of them. What the Lambert law was saying was talking about more light will be absorbed as you increase the thickness. Thickness means like when you have a cuvette or any sample holder, they have a specific length. So if you have got 1 centimeter cuvette, the light will pass through that and a particular amount of that will be absorbed. But if it's a 2 centimeter long cuvette, so that pathway has increased, so definitely more light will be absorbed. And similarly here in the Beer law, it directly relates with the concentration. More the concentration of the sample, like more molecules are there. So when the radiation passes through the sample, when there are more molecules, they will absorb more light. So more the concentration, more light will be absorbed by the sample. So these are the two laws that we combine as Lambert and Beer law, and these two laws are the basic fundamental laws apply in the spectroscopy. So going back to what you guys have already done in spectroscopy, and for example, you have a unknown sample which you have to determine, and then you have a couple of standards which you already know their concentrations are. So if you recall, like you guys make the standards like S1, S2, S3, S4, S5, and what was the criteria? Increasing concentration. So S1 was of the least concentration in terms of that whatever molecule it is, for example, glucose. Then S2, S3, S4, S5, it's the gradual increase of the concentration of that molecule. And when you measure the OD of such samples in the spectroscopy, you can recall that with the increasing concentration, the OD increases. Why? Because there are more molecules in the sample and they are absorbing more light. So this is how it goes. Most of the time, the factor of the cuvette length is kind of a constant, which in most of the cases is 1 centimeter. But we understand that more the path length, more will be the absorption of light as well. But that's not mainly being considered as the major factor. So that's about the Lambert and Beer law. Now we start towards the principles of uh, the UV visible spectroscopy, the ultraviolet visible spectroscopy. So as I mentioned in the spectrum earlier on that the regions are different. You know about the visible region between 400 to 800 nanometer. The UV radiation region actually extends from 10 nanometer to 400 nanometer. That means just before the visible region starts. So then there is a called the near UV region, which is between 200 to 400 nanometer, which is not actually important at this stage for you. And then there's a far UV region, which is below 200 nanometer. So this is, I would say, further differentiation of UV into two regions. This UV from 10 nanometer to 400 nanometer is further uh, divided into two regions as near UV and far UV. And I think the term itself are self-explanatory what actually near UV region means and far UV region means. So the far UV spectroscopy is studied under the conditions where you have vacuum. Now this is very important thing that when you perform the UV spectroscopy, specifically the far UV spectroscopy where you're using the electromagnetic radiations of the wavelength below 200 nanometer, there is a prerequisite that you measure or you do that spectroscopy under the vacuum condition. The common solvent that we use for the preparation of the samples to be done by far UV spectroscopy are either ethyl alcohol or hexane. These are the two most common, sample preparing solvents which are used for far UV spectroscopy. Uh, Now, regarding the transitions, I already have discussed with you. This picture indicates you that how the electronic transitions takes place. And I'm sure that in general chemistry, you guys are aware of the fact that how this electronic transition takes place. When you provide energy, the electrons in the outermost shell are the first one to absorb that energy. And once they absorb the energy, they will be raised to a higher energy level, what we call the excited state. If you carry on, providing that energy, they will absorb more energy and will jump to even higher state. But the important thing is that when electrons are being provided with the energy and they jump on from a lower energy to a higher energy level, they are in their excited state. And in the excited state, electrons are unstable and they cannot remain there for a longer time. So what will happen that once they have absorbed energy and jump to a higher energy level where they are excited and unstable, they are going to release that energy to come back to the normal level. So it's kind of, absorbing and emitting energy from, changing from lower to higher energy and from coming back from higher energy to lower energy. And that particular term is being referred to as electronic transition. And you can see in the picture that energy in terms of the photon HV1 is absorbed, and then we have energy which is being emitted as HV2 and HV3, and with the release, they will go back in their lower levels and finally reaches the ground state. Now, a little bit of details about the possible electronic transitions, a little bit of more detail, just not in terms of the shells, but a little bit of more detail. You can see that on the x-axis we have increasing energy, and with the increase of the energy, we can see the transition going on. And if you start from the lower side, you can see that the bonding electrons are the one having the least energy, and they are the one which are the most stable, because stability is inversely proportional to the energy. So at this stage, when you have got the least energy, the electrons at this stage, they are called as bonding electrons, and they are the most stable. Now as you go on increasing the energy, the electrons will absorb the energy, and here comes the transition, because now they absorb energy and they are doing the transition, they are going up. So from bonding, they reach the level of uh, pi bonding, which is the next higher level. Definitely, this is a little bit unstable state as compared to this one. And then if this process goes on, you got the non-bonding, and then you got entire bonding pi, and then you have got entire bonding sigma. So this entire bonding sigma is the highest electronic transition when they absorb energy. And as I said, similarly, the electrons cannot stay here longer because they are unstable. So there is a way to come back, and when they come back via the same route by releasing the energies. So you can see that it's from bonding to sigma bonding to pi bonding, and then pi bonding to non-bonding, then non-bonding to pi anti-bonding, and then sigma anti-bonding. So these are the transition levels being shown graphically in front of you. This is another diagram, the same one in a little bit different way. These are the 6 levels here, and they are being shown in a different way here. So you can see that the transitions could be possibly of 6 types. The first transition is from sigma to sigma star. The next one is from pi to pi star, then non-bonding to sigma star, then non-bonding to pi star, then sigma to pi star, and then pi to sigma star. So these are 6 possible electronic transitions that could be as a result of absorb of energy by the electrons. So now we have to go in a little bit of detail of all these 6 possibilities. And what I'm thinking about is most probably I'm going to finish up once I'll go through all of these 6 quickly, because that's not going to take much of the time. So the first possibility is from sigma to sigma star. As I said, that sigma electrons, if you go back to this picture, you can see that the sigma bonding electrons are at the least energy level. And as I repeatedly said, that they are the one which are the most stable. So the sigma electrons from the orbitals, they are excited when they absorb energy. They are excited, and they are excited to an anti-bonding orbital called sigma star. The energy which is required to do this transition from sigma electron to sigma star anti-bonding is large. That means you need reasonably large amount of energy to do this transition from sigma to sigma star. The example of that is a methane. Methane molecule has got a carbon hydrogen bond, because there's 1 carbon and 4 hydrogens, so all the 4 bonds are identical. So in this case, it has got only single covalent bond between carbon and hydrogen, and it can undergo from sigma to sigma star transition, and it shows absorbance maximum at about 125 nanometer. So you can see that this transition from sigma to sigma star, the example given is of the methane, and this will give you an absorbance maximum of about 125 nanometer. The second transition was from pi to pi star. Now in this case, the electrons naturally reside in the state of pi electron, and they are bonding orbital. Once they absorb energy, they are excited, and they move on to anti-bonding, which is pi star. Now, for this particular transition, the compounds with containing multiple bonds, like they have single bond and double bond and triple bonds, these sort of compounds, for example, alkenes, alkynes, carbonyl compound, nitriles, and aromatic compound, etc., 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 they do have this kind of transition. And I'm sure that you guys recall the basic concept of the organic chemistry that you guys have studied, that single bonds are called sigma bond, and the double bond is called pi bond, and when it's a triple bond, then it's 1 sigma and 2 pi bond. So if you can recall that from your organic chemistry. So the compounds having a double or multiple bonds will undergo this kind of transition. And for example, talk about alkenes, the region that they absorb will be falling between 172 205 nanometers. So for this transition, it was maximum at 125 nanometer, and for this, the range is between 170 to 205 nanometer. Let me tell you that what these ranges are actually. These ranges are actually the range of the wavelength where they absorb maximum amount of radiation or energy. Then we have the third transition, which is from non-bonding to sigma star transition. This is particularly in case of saturated compounds. Now, methane was also a saturated compound, but this is a different category. These are the saturated compounds containing atoms with a lone pair of electrons. For example, if a molecule is a saturated molecule, but it contains oxygen, nitrogen, sulfur, and halogens. They do have, lone pair. We know that oxygen, nitrogen, sulfur, and halogen, they have lone pairs. So the molecules which are saturated, but they have the elements having the lone pair of electrons will undergo that transition from N to sigma star. These transitions usually require less energy because the difference of energy between these two transitions is less. The number of organic functional groups with this N to sigma star, they undergo their maximum absorption within the range of 150 to 250 nanometer. The fourth one is from non-bonding to pi star. Now, for this kind of transition, an electron from a non-bonding orbital is promoted to an anti-bonding pi star orbital. This kind of transition uh, exists in the compounds containing double bond involving heteroatoms. Now, this is another important thing. Like in previous cases, we talk about alkenes, we talk about alkynes. They do have double and triple bond, but that is between two similar atoms. Here we are talking about the double bond between the heteroatoms, like between carbon and oxygen, carbon and nitrogen, nitrogen and oxygen, and so on and so forth. So they particularly undergo this kind of transition. For this transition, they also require minimum energy, and they show absorption at a longer wavelength of around 300 nanometer. Then we have the fifth and the sixth, which is sigma to pi star, and then from pi to sigma star transition. This kind of transition, these electronic transitions are forbidden transitions, and they are only theoretically possible. So that means it's out of the box when we talk about spectroscopy. It's theoretically one possibility, but it do not exist as practically this transition takes place. So thus, from N to pi star and then pi to pi star, the transitions, they show absorption between 200 nanometer, which is accessible to the UV visible spectrophotometer somewhere in between, and the UV spectrum is of only a few broad of absorptions. So this fifth and sixth transitions are only theoretical, and they are not practically possible. So I'm going to stop my lecture at this stage just to quickly summarize these, six types. And what I actually wanted to convey is we got an idea that these six kind of transition, rather I would say the first four kind of transition that we discussed, and we had given you certain examples. So from this, what we understand that if we know our compound for which we are going to do the spectroscopy, we can predict which sort of electronic transition it will undergo. Like if it's methane, we know. If it's alkene and alkynes, we know. If it's a compound with a double bond between hetero elements, we know. So this if we know the nature or the chemical structure of the compound that we are doing the spectroscopy, we know that what sort of transition it will undergo. And based on that, we know that what is the wavelength at which it's going to absorb maximum radiation. And that's how, going back to the topic, when you guys have done your spectroscopy in first year and second year, if you remember, in the practicals, you have been told a specific wavelength where you absorb the light. And we know that that particular wavelength is the one where these compounds are going to absorb the maximum. So that's how this is going to help out in determining what sort of spectroscopy what sort of electromagnetic radiations, what sort of wavelength is used to determine the absorption of the light by different compounds depending upon their chemical structure. So I'm going to stop here, and inshallah, in the next class, we'll be continuing this, and most probably we'll be finishing this in the next class, inshallah. So if you have any question by now, I would ask you to raise your hand if you have question, and I'll go through one by one to answer your question. So if there is any question, just raise your hand, please. I think most of you guys are sleepy. That's why you're not asking the questions. Or either way, I think the things have been explained and well understood, so you don't have any question. So I would be optimistic as well. But if you do not have a question at this stage, go through the presentation I'll share with you, and go through this lecture again, and come back to me if you have got any question anytime. And do give your feedback in the WhatsApp group about today's lecture. Like, was it a slow pace or a fast pace, or what sort of challenges you faced during the lecture? So if you have got any concern or any feedback, then please share with me, or in the group, or in person, whatever. So I'll definitely try to overcome those challenges, inshallah. So if you do not have any question, I'm going to stop the class here, and inshallah we'll share the recording with you guys soon. Thank you very much. Take care of yourself. For the Hafiz.